We're going to talk about melting point theory here. Now, in organic chemistry, we can use the melting point of a compound to elucidate the identity of a solid unknown. It's kind of a typical thing to do in an organic chemistry lab. And then more commonly, we use it to determine the purity of an isolated product. So we synthesize a target compound, aspirin, for example, and to determine the purity of aspirin, we take its melting point. In order to comment on the purity of the compound, though, we have to compare our experimentally determined melting point with that of the true compound's melting point. Now, the melting point, a true melting point, is the temperature in which the solid and liquid phases of a pure substance are in equilibrium. All right, now this should just be one number. Now, the capillary melting point is what we are going to see when we take the melting point of a compound in lab. And this is a range, and it's the range over which a sample of a compound in a capillary tube liquefies. It's fairly easy to measure. It starts when the sample begins to liquefy and ends when it's completely liquefied. And one reason why we don't get a precise exact number is because we just don't go slow enough to see a precise number. So we continue to heat through essentially the melting point and we get a range. Now, in general, pure compounds have melting point ranges less than that of about 2 degrees Celsius. Ranges greater than 2 degrees Celsius indicate the presence of impurities. The other thing that happens is when we have impurities present, depressed ranges are going to be seen. So we're going to see two things with impurities: a lower melting point and a wider melting point range. Now, technique-wise, your technique can also give you larger and depressed ranges. So we'll have to practice this as a skill as we go through and learn how to take melting points. Now, in this experiment, we'll do a few things. We're going to take the melting point of a known just to gain expertise. So we'll pick a known compound and we'll get to kind of learn how to use the instrument. Now, once we're good with that, you'll be given an unknown. And the unknown will be from a list of a table, essentially. And our first goal will be to narrow our choices to 2 compounds. There's like 15 or 16. And to do this, since we don't know the exact melting point range, we will go fast to get a rough idea of the melting point range, and then we'll take a more precise, slower melting point. Now, it's kind of like, if you remember from general chemistry, you would do titrations. You wouldn't start off just adding, 1 drop or part of a drop at a time. You would just add a whole bunch of acid or base in there, right? Get your color change, and then you might do like a back titration or something, right? But at least you'd know roughly what the volume was. So again, we'll do a fast melting point. That'll give us a 10 degrees range. We'll allow the instrument to cool, and we'll take a precise measure. In our lab, your unknown will be one of the following compounds. So if you look over at the left column here, you see the approximate melting point, and you'll see that they're grouped together in groups of 2, right? Oxalic acid dihydrate and toluic acid both have melting points about 102, right? All the way down to paraphenylphenol and triphenylmethanol, which have melting points about 164. So you'll take a melting point quickly to determine roughly what you have, right? So you might get a melting point of 90 to 105, and then you'll take another melting point and you'll get something more accurate. But nevertheless, what you'll find is that you'll get yourself narrowed down to a group of 2. Now, you're going to have to narrow your choices to 2 compounds. So let's say that you get a slow or an accurate melting point of 131 to 134, right? Maybe you could get that a little bit more narrowed too, right? So you could get a 2 degrees Celsius range in there. But nonetheless, if you found this to be your melting point, you'd look at this table and you'd say, well, look, 133, right? And 133, here you have urea or you have tranexamic acid. So your unknown is going to be one of these 2 compounds. Now, how do you determine which one of the 2 you have, right? Because they have identical melting points. Well, if you look over at the right-hand column, some of these compounds, in fact, in every group of 2, one of those compounds will be available for you in lab to do a mixed melting point with, right? So you've got this unknown, and you need to do a mixed melting point. And for this choice, right, the choice of these two, the only one that's available for you to do a mixed melting point with would be urea. So we do a mixed melting point with urea. Now, why do we do a mixed melting point? So let's talk about that for a second. So we're going to create a little diagram here where we have temperature on our y-axis and percent composition down here on our x-axis. And over on the left-hand side, we have 0% B, and on the right, we have 0% A. Now, let's just mark here a couple melting points. So melting point of A will have just being lower than the melting point of B. We just chose this arbitrarily, so it doesn't really matter. So if you have pure compound B, it's going to have a melting point. And as you add more of compound A to it, it tends to lower the melting point. Remember we said in the beginning, an impurity lowers the melting point and makes the melting point range a little bit broader also. So that number is going to go down. But it's not going to go down forever, right? So at some point in time, it's got to kind of come up here and meet melting point A, right? So when we have melting point A, if we add a compound to this, compound B, that melting point goes down too. So they continue to kind of go down, but they're going to meet at some point. And that point down here, we'll see in a minute, is called the eutectic point. All right, so again, adding an impurity will lower the melting point. So how do we read this graph? Well, if we pick this percent composition, right, like let's say we are given a capillary tube or a sample that had this percent composition, right? We would take that, we'd pack it in a capillary tube, and we'd start to melt it. And what you'd notice here is you start to heat up, right, because temperature is increasing this direction. So as we walk up this, we have solid A and B, but then at some temperature, that is going to start to melt. So what we're going to see, when we look at it through a magnifying glass, we'll see that the sample starts to get kind of sweaty. So we call that sweating, and that's the first drop of our liquid. Now, in the middle here, then, we have a mixture of a solid and a liquid. We're undergoing a phase transition here, right? And because we're continuing to heat, we see a little bit of a lag here, right? But we see heat going up, and at some point in time, we're going to witness the last little bit of that solid. And when that solid, that last little piece of solid disappears, it kind of looks like it's dissolving, but it's melting. We call that complete melting, right? And that range right there is your melting point range. So this is why we see capillary melting points listed as ranges. Now that little point down there at the bottom, that thing again is called your eutectic point, right? And if you continue to heat beyond that, which you certainly can, your capillary tube would just be filled with liquid A and liquid B. So by adding an impurity to our compound, or by doing that mixed melting point, we're going to witness one of two things. So let's look at our example again. Our unknown, if we mixed it with urea and the melting point was depressed, that would mean that your compound was not the same thing as urea, right? So, of course, if you mix urea with urea, the melting point should be the melting point of urea, right? So if you have your unknown and you mix it with urea and the melting point was depressed, your unknown would be tranexamic acid. If your unknown was mixed with urea and the melting point was essentially the same, then your unknown would be urea, right? Because you'd see no depression there. Now, how do we take a melting point? So when we're in a lab, what do we do? Well, it's fairly straightforward. You're going to obtain a capillary melting point tube. So there's this little tube in lab. You'll grab that, pop the top off, and you'll pull out a melting point capillary tube. So they're about this size. Here's a paper clip for a size comparison. I want to point out to you that on one end, we have a closed capillary tube. On the other end, it's open. Sometime in labs, we have capillary tubes that we use for thin layer chromatography. And those are going to be open on both ends. So don't grab one of those because you're not going to be able to hold your solid, right? It'll just move through one end when you pack it into the top. So you're going to get a capillary tube. Okay, closed end, open end, make sure you're watching out for that. And then you're going to take your sample and you're going to grind it up. You can use a mortar and a pestle for this. So sometimes we'll use a watch glass in the closed part of a test tube, but grind it up, and then you're going to take the open end and you're going to pack in some of that material into the open end of your capillary tube. And then we have these long tubes in our lab. They're open, and you're going to put the closed end down and you're going to drop it. When you drop this in, it's going to come down and it's going to bounce up and down in here. And as it bounces, that solid that's stuck up here at the top is going to make its way down into the bottom of our melting point capillary tube. So how much do we add? Well, we want to add about 2-ish, maybe 3 millimeters worth of sample. So, sometimes we'll do synthesis, for example, and your yields are going to be really, really low, and you might be happy to have this much. All right, and then you just deal with it. But we want to try to get about this much. This is too much and this is a waste. So something around there is what you're shooting for. All right, now we're going to use these things called Thomas Hoover melting point apparatus. And it looks like this in the front. So you can see there's a temperature adjustment here. There's an on and off switch right here. This knob right here controls the stirring of the oil. So inside of this instrument, there's a coil that heats oil that's inside of a beaker, essentially. Now, if you look at the top of this right here, you'll see that there's 1, 2, 3, 4, 5 holes. And what you're going to do is you're going to put your sample right there, right in the middle. And then we control our temperature here by adjusting this knob. And what we're going to be looking for is a nice rate of heat. And we'll be looking through this magnifying glass to determine when that sample actually starts to sweat. And then we'll come up and we'll look at our thermometer, and that will be the beginning of your melting point range. We continue to heat, and then at last, finally, that last little piece of solid, it melts. Then we look back up and we record our temperature, and that's the end of your melting point range. Now, as you start to heat, what you're going to be looking at is something like this. This is a magnified view of what you're going to be looking at with the capillary tube. So here's a sample. You start to heat, and pretty soon you start to see a little bit of sweating, right? So that sweating is when you start to record your initial temperature, and then you keep a careful eye on it, and you notice the last amount of that little solid eventually melts, and that will be your ending melting point range. Now, once you're done with that capillary tube, you're going to take it out and you have to discard it. So you can't take that capillary tube sample that's been melted and let it cool down and remelt it. So a lot of organic compounds, when you heat them up, they can react with oxygen in the air, they can decompose, they can do all sorts of things, but we always pack a new capillary tube if we have to take a second melting point.